cord for Amy. So, we added some lye to some water, and what did you notice?
It got warm.
It got really warm. So if you mix something together and heat is given off as a product, that's called an exothermic process. Exo means heat, so it gives off heat. So, or exo means out, therm means heat. So exothermic means it gives off heat. If something uses up heat in the process, that's called endothermic, E-N-D-O, there on page 364. So a process that gives off heat is exothermic. A process that uses up heat is endothermic. So I'm sure you've all used a cold pack before, right? Or you crack it and you can put it cool your arm or your knee or whatever. Those are all endothermic. They use up heat, so they get cold. Something that gives off heat, they sell those for your back too, or sore muscles or whatever. You crack it or do some sort of, there's a chemical reaction. Maybe, usually there's a vial in there you crack and then you shake it or something. And you apply that, it gives off heat, exothermic. So just know the difference between exothermic and endothermic. Let's see, what else? So we should clarify, last week we did solubility. So remember, when you're mixing a solute, your solute can be a solid or a gas. It can even, if you're mixing something in, a solute is what you mix into your solvent. Your solvent would be, in this case, you had water, and your solute was lye, right? We mixed lye into the solvent that was water. Or we have salt and water. So your water, again, is your solvent, and your solute was a solid salt that we put in there. So just keep track of what's the difference between a solute and a solvent. So make sure you know that lye is exothermic. So write up one of those labs. If you want to write up the one, make sure the first one, make sure you tell me what exothermic is. You might want to mention endothermic. And if you write up the other one, you're going to need to know the temperature difference between the salty one and the not salt one, because they should be different. All right. I'm afraid I'm going to run out of time, so I'm going to skip to molality on page 367. And if we have time, we'll come back to 11.1. So we learned something before, maybe you don't remember, but we did a big M, which was molarity. And does anybody remember what that was? Anyone? It's how many moles per liter of solvent, right? So a mole of solute, so like if you figure out how many moles of salt we put in there, and if we had a liter of solvent, a liter of water, or convert it to liters, we only had, 50 mils, I think, in there. But you can figure out the molarity. It's how strong a solution is. So apparently there's a shortage of letters, and so they use, that's a capital M. Now we're going to do something which is a small m, which to me in the past has meant meters, right? But this small m is actually going to be your molality. Molality, can you get any closer? I don't know. So same letter, really close, but they're measured a little bit different. So the small m is going to be your moles of solute, so that's kind of similar, over your kilograms of solvent. So how do you know which one you use? Well, if they gave you a measuring that's in liters or milliliters, you can calculate the molarity. If they tell you that you have 100 grams of water, you're going to know that you're doing molality. It's going to be the big difference. So, so the top both is moles, but If you're talking about liters or milliliters, your molarity, capital M. If you're talking about weights, grams, kilograms, you're going to be doing kilograms of solvent. It's not the whole thing, it's just how much solvent you have, how much water or alcohol or whatever liquid you're putting it into, and that's going to be your molality. Okay, so let's do example 11.2. A chemist mixes 3.4 moles of sodium chloride, NaCl, which is what we're using today, salt, sodium chloride, with 4.5 kilograms of water. Oh, they measured the water. Must be talking about molality. Okay, what is the molality of the resulting solution? So remember, M equals the moles over kilograms of solvent. So it's going to be just 3.4 moles of NaCl over it's already in kilograms, so we don't have to do any conversions. Sometimes it's in grams. You might have to convert from grams to kilograms, but it's 4.5 kilograms of water. So calculator, 3.4 divided by 4.5 is going to be 0.76, and it's a small m. Okay, so it has a molality of 0.76. So the next section of the example, it's the same thing, only it's 45 grams, so you'd have to convert your moles first, right? With your periodic table, you'd look up how much zinc chloride, so how much zinc is, plus 2 chlorides, and you'd first have to convert that to moles. So just know molality is going to be in kilograms. Okay. So last week we did, what did we do? We put something in the freezer with some salt, didn't we? And so we put it in a saturated solution in the freezer, and so you couldn't see any salt. And then we lowered the temperature, and then all of a sudden, hopefully you saw the picture that I sent you because we forgot to look. There was some salt in the bottom, right? So the saturated solution, when it was hot, could hold a lot more salt than when it was cool. A solid solute the solubility is lower as long as when you cool it down. So if you want to increase the solubility for a solid in a liquid, you're going to heat it up. If you want to increase the solubility of a gas in a liquid, you cool it down. So we decrease the solubility by cooling it down. So today we're adding salt to water, and we're going to see which one freezes better, or what happens to the temperature. So we're using a temperature. We're going to see a temperature change. So how you write temperature change is, I don't know if you've done this in math at all, this little triangle means change in. So change in T means the difference in your temperature. So we're going to be talking about freezing point depression, how to lower the temperature of something, or boiling point elevation, so how to make your temperature higher in something. So it can still be delta T both times because it's the change in the temperature. So the freezing point depression is based on, you can see this, is based on this letter called I. It's how many ions something can break into. When I put a solute into a solvent, remember we had this cool picture last time. I don't know if it's cool. It's better than me trying to draw it. So that way it's cool. Where remember when I put salt in water, it breaks into a number of different pieces. You get the sodium pieces surrounded by water because they're positively charged, and you have your chlorine pieces and they're surrounded by water because they're negatively charged. So sodium chloride, NaCl, breaks into the positive part and the negative part. So it breaks into two pieces. But some other things like, oh, I don't know, sugar or something that's covalent, or a polyatomic ion, because polyatomic ions that you've memorized, I'm sure, because you made note cards over Christmas and memorized it. But the polyatomic ions, they stay together in one group, or something that's covalent, they stay together in one group. So they have big chunks that are, the whole chunk is surrounded by water. They don't break into different pieces, and that makes a difference. The number of pieces that they break into affects how your boiling point will be elevated or how your freezing point will be lowered. Does that make sense? The more pieces you have, the lower it can depress your freezing point. The more pieces you have, the higher it can make your boiling point. So we learned this week. When you have ice outside like we had this week, what do? You put salt out there. Why? Because it lowers the freezing point of your ice and it melts your ice. So sometimes you buy something called ice melt. You pay a lot more money for it, but what does it do? It works better than salt because it breaks into more pieces and it lowers the temperature even more and it melts the ice even faster. That's how it works. Science. It's cool. So just keep in mind that the number of pieces something breaks into affects your freezing point or boiling point. So the formula for this is I, but it's freezing point depression, so we're going to lower the temperature, so it's going to be a negative I. So negative the number of ions that your thing breaks into, times K sub F, which is just, it's going to be your, what's it called? Freezing point, it's a constant. So they have to give you the K sub F or the K sub B if it's a boiling point. So it's a constant depending on what you're talking about. So they'll have to tell you that part. So you have to memorize this. Negative I times the K sub F times the small m, which we just learned, is the molality. Okay? So this is the freezing point depression. I know it's freezing point because this is K sub F, and they're going to give you the K sub F in any problem. And I know it's lowering the temperature because this is a negative I. Okay? If we want to raise the temperature, it's going to be similar. It's going to be your delta T equals positive I, same thing, only this is not lowering my temperature, it's raising my temperature. And it's going to be K sub B, which they will have to give you, and times, again, the molality. So it's basically boiling point elevation, how to make your temperature change higher, freezing point depression, how to lower your temperature. It's really just the different constants that they're going to give you, and this one has a negative I, this is a positive I. So let's do one. Example 11.3. When 15 grams of sodium chloride are added to 100 grams of water, what's the change in the water's freezing point? Change in the water's freezing point, so the delta T. So we're going to, we have to figure out the I, so it's going to be, I'm going to scooch it over. Delta T is going to be my I. Did they give me the I? No, but they told me that it's sodium chloride, so NaCl. How many pieces does NaCl break into? It's ionic, and this is a positive part, and this is a negative part. Guess how many pieces it'll break into? 2. Okay, your answers are going to be like 2, 3, 4, 5. If you get more than that, probably it's a covalent compound, and it doesn't break apart at all, and it's going to be 1. Okay, if they give you a sugar that's like C12, it stays together in one piece. The answer is 1. Okay, so really it's only if you have an ionic thing. Remember how you know something's ionic? You have something from the left side of the periodic table and something from the right on that zigzag. So that's your thing, so you gotta check in the freezer. So that's how you know something's ionic if you don't remember. So let's do this, that's gonna be big. All right, so first we had to figure out, this is how many moles per kilogram. So we're going to they gave us the grams of water, and so we have to figure out how many moles of sodium chloride we have. So let's do that first. So if we have 15.0 grams of sodium chloride, first we got to find out how many moles we have. So how do we do that? We look at the periodic table, look up sodium, look up chlorine, and we figure out that that together weighs 58.5 grams in 1 mole. So that means we have 15 divided by 58.5 is 0.256 moles of sodium chloride. They told us in the problem that we have 100.0 grams of water, but we need to know how many kilograms of water. If you can do that in your head, that's fine. If you can't, know that in 1 kilogram, there are 1,000 grams, which means I move my decimal place over 1, 2, 3 places. So that means I have 0.1000 kilograms of water. So my molality is going to be moles per kilogram. Okay, so if I divide 0.256 over 0.1, I'm going to get 2.56 mole. Okay, so am I done? No, now I have to go back. That's just this part here. So I have to go delta T, the change in temperature, is going to be my negative I, which we said sodium chloride breaks into 2 pieces. So -2 times this case of F that they have to give you. It's 1.86 degrees Celsius per M. And this is your M, 2.56 M. So this M cancels that M off. The only unit you have left in this is degrees C. So this means that if you take -2 times 1.86 times 2.56, you get, I don't have my calculator here, -9.52 degrees C. This is a perfect number, so that doesn't factor in for your significant digits. This has 3, this has 3, so I get 3 answers, 3 places in my significant digits. So your answer is, the question said, right here, the question said, what is the change in the water's boiling point? This is the change. It lowered it 9.52 degrees C, okay? Sometimes they're evil, and they don't want the change. They want to know what the new freezing point would be. So whenever I'm done with a question, I go back and read, did I answer what they said? This is the change in the temperature. If they say, what's the new temperature? Well, then I would have to know water freezes at, anybody know?
100 degrees Celsius.
What?
100 degrees Celsius.
Water freezes at 100? Doesn't freeze at 100.
Boils.
Okay, boils at 100, but it freezes at 0 degrees Celsius, right? So don't get confused that it's 32 degrees Fahrenheit, but it freezes at 0 degrees Celsius. So if it said, what's the new temperature? Well, 0 minus 9.52 is still going to be -9.52. But sometimes it's not. And I know on the test, one of them, they tell you that it's a different solvent. I don't remember what it is, alcohol of some sort. And they say that it freezes at -10, and then they say, what's the new temperature? Well, don't forget to subtract that. Subtract your change from the original. It's kind of evil, but just read your question. Okay? Schulte, go lay down. All right, let's pause here and see if we have a temperature change in your water. So let's look at, see if there's any. I don't see anything freezing yet. Let's let it go for another few minutes. Because one of them should freeze and one of them should not freeze. Maybe you can guess which one it is. So, don't let me forget it though. Okay, let's do what's the freezing point of a solution? So again, we're gonna leave that there. Did I lose anybody? There's a lot of steps, but the formula is the same. And the way you get they should give you all the pieces. So you should be able to see in the problem when you're reading it, all the pieces that you're gonna need. There shouldn't be any surprises. The hardest thing, and you get a point on your test, I know when I'm grading it, one of the points is figuring out what your I is. So we're gonna practice figuring out I. But what's the freezing point of a solution made by mixing 2.5 grams of AlNO3, and there's 3 of those, and 150 grams of water. Okay, and then they gave me the case of F. So, where do I start? Well, I need to figure out my small m, which is how many moles per kg. So I have to convert this to kilograms, so that we know how to, again, you're just dividing by 1,000, so move your decimal place over 3 places. So if I move my decimal there, now it's kg. If I have 2.5 grams, I have to convert it to moles. So I'm going to do 2.5, grams times how many grams are in 1 mole. And this one's a little trickier because you have to take 1 aluminum. How many N's do you have? 3, because it's 3 times that. How many O's do you have? 9. So that's going to be the hard part. How can you figure out how much that weighs? So you're going to look 1 of those, 3 of those, 9 of those, and figure out how much 1 mole of it is. So I'm cheating, and that is 213.0 grams. So that's going to be 0.012 moles divided by your kilograms, 0.1500 kilograms. And if you put that in your calculator, you'll get an M of 0.080 M. Okay, so that's that part there. Now the case of F they gave you, it's 1.86. So the hardest thing now is to figure out your I. So if we have, remember, Al, the parentheses means that it's a polyatomic ion, right? You've memorized, I'm sure. You know that one. You've memorized it, right? Sure. So what does that mean? That means there's 3 of those groupings. That means it looks something like this with NO3 here and NO3 here and NO3 here. Because it's 1 aluminum, it was Al, it's positive 3. These nitrate groups are negatively charged, so it looks something like this. So how many pieces does it break into?
4.
Here's 1, 2, 3, 4. If you know that the thing in the parentheses stays together in 1 chunk, count how many pieces you break into. So your I, your how many ions, is going to be 4. Okay, so that means I sprinkle this out on my ice. It's really going to lower my temperature. So, and we put it all together. So delta T is going to be -4, because it broke into 4 pieces, times the case of F that they gave me, 1.86 degrees C per M, and the M that I calculated, but I erased, and so it was 0.080 molar. And my M cancels out, I'm left with delta T, so 4 times 1.86 times 0.080 is going to be -0.60 degrees C, which doesn't seem like it lowered it very much, but you didn't have very much of it, right? 0.08 moles, not that much. So, but it said, if you go back and read the question, it says, what is the freezing point of the solution? So this isn't necessarily your answer. Well, it is though, because this is again water, right? With water. So it's water, freezes at 0, so then you subtract 0.060, so it is your answer. But again, if your solution wasn't water and it froze at 10 degrees, it would be 10 degrees minus this. So just be careful, because I know they're evil on the test, and they have one like that. Okay. So I'm not going to do the whole next one, because this part is all the same. Let's just practice. What's the freezing point of a solution made by dissolving 100 grams of table sugar, C12H12O11, into 950 grams of water? Still going to have to figure out how many moles you have, divide your moles by your kilogram of solution. They gave you the case of F, but what's your negative I? Well, it's sugar. It's C12H22O12. Oh, sorry, 11. So does that break into 12 and 12 plus 22 plus 11? No, it doesn't. If you get a number over 5, probably it's covalent and it stays together. Remember, that's the picture where it stays into a chunk and water goes around the whole chunk. Anything that is covalently grouped together, and polyatomic ions stick together like a covalent molecule. It's got a charge like ionic, but it sticks together as a covalent molecule. Your I is going to be 1. Okay, so it's going to be -1 times the case of F that they gave you, 1.86 degrees C per M. You're going to have to figure out the hardest thing here is going to be figuring out how many grams per mole, because you have to have 12 carbons and 22 hydrogens and 11 oxygens, so it's a big molecule. Okay, so if you want to lower the temperature of your ice, don't sprinkle sugar out there. Sprinkle some salt. Okay, so boiling point elevation, same exact thing. Only now you are raising the temperature, so your I is going to be a positive I. They still have to give you this constant, and it's just now called a case of B. It's the boiling elevation. This is the freezing point depression. So this lowers it, this raises it. So they have to give you a different case of B. You figure out your M the same exact way. So let's just, I'm going to give you some different things, and I want you to tell me what you think your I is, because again, on each of the problems on your test, you have to figure out the boiling point elevation or the freezing point depression, but one of the points of that is figuring out what your I is. So if you get your I wrong, but you figure everything else right, I only take partial credit off. But let's practice finding your I, because it's really pretty easy. If you can figure out polyatomic ions stay together, covalent ions stay together. Okay, so if you have CaNO3, 2, what's your I going to be? Guess.
3.
Is he right? You're going to have a calcium. You're going to have 2 nitrate groups. Is he right? Yes, he is. High five. So your I is going to be 3. How about anything in a parenthesis, it stays together. How about CCl4? How many pieces? Bless you.
Thank you. 5.
Is it 5? Is he right? Is he right? No, and I'll tell you why. Anything that starts with a C is carbon-based, and it's covalent. Remember, look at your periodic table. Where's carbon? It starts over here. If your first atom in your grouping is over on this side, it's covalent. Okay, anything ionic is going to have a positive thing from this side of the periodic table and a negative thing from this side of the periodic table. If you have something that starts with carbon, I guarantee you it's covalent. Okay, so what's my I?
4.
1.
1. Dang.
Okay,
That was my next guess.
1. Yes, and it would have been right.
13.
Okay, so how about I mean, if you get something like 22, you know it's covalent, right? But 5 is close. You never know. You might get a 5 for an ionic thing. How about MgF2? Where's MG? MG's here. So how many pieces does it break into? 3. So your I is going to be 3. How about C2H6O2? 1. Anything starts with C, it's got to be covalent. So I is 1. How about MgOH2? 3, because it's going to be a Mg, and it's going to have an OH group, which is a polyatomic ion that you've memorized, with an OH group, polyatomic ion. Here's 1, 2, 3. Breaks into 3 pieces. If it's got a parentheses, the thing inside the parentheses doesn't break apart. Okay? How about CaCO3? This is kind of a harder one. This is probably the hardest one. Where's Ca? That's over here.
5.
Would be a good guess, but I'm sure you've memorized that COC3 is a polyatomic ion, so it could have a parentheses around it, but it is only one grouping, so they only have 1. So this is going to be your hardest one. It's carbonate. It's a polyatomic ion. So what's your group? What's your I? 2, because it breaks into a positive calcium and a negative carbonate group. So your I equals 2. Okay? Probably the hardest one. All right, last one. C12H22O11.
1.
Yes, because it starts with carbon. So it's covalent, stays together in one piece. Okay? So figuring out your I is not hard. If you remember your polyatomic ions stay together. If you remember if it starts with carbon, it's going to stay together. So it's 1. Okay? So there's 2 formulas you need to memorize. Again, delta T equals negative I if you're lowering the temperature, K sub F, times your M, and delta T equals I if you're raising the temperature, K sub B and M. And remember your M here is going to be your moles over your kilograms of solvent. So the weight of your water that you're mixing it into. Okay, so now let's look at our things. Let's see. How warm was the water you used? Well, we'll see if there's a temperature change. So, who wants to? We could assume these are both, maybe, hopefully these both read the same. Let's see if they're the same temperature to begin with. This is at what? Can you read that one? Maybe if I open the right side.
20.
Okay, that's a 20. Let's see what this one says. I use my teeth, but that sounds disgusting. What's this one at? Oop, it's not. What's that one reading?
Oh, no, like 18.
Yeah. So they're not reading exactly the same. So, well, actually now this is saying 20. This is 20. All right, so maybe. So let's see if there's a temperature change between, this one was the salt water. I can see a little bit of salt coming up, but not much. And we'll see if there's a temperature change in them. So, all right, somebody want to read them? They shouldn't be exactly the same. Who wants to read it? Anyone?
I will.
You're close? All right, what's that one say?
It's like 2 or 3.
All right, and what does this one say?
That's like -1 or 0.
So,
Or no, that's 5.
so, which one is colder? Which one is colder then?
That one.
This one is colder. This one is. Well, actually, it looks like 4. What's this one? This one is 0.
So this one.
So this one is the temperature is higher because it has ice. I mean, it has salt in. This one, the temperature is lower. It doesn't have salt in. So does that make sense? If I wish one of them would have ice in it. So if this is 0, it should be really close to being made into ice. And this one is less close to being made into ice. Does that make sense? We put salt in, so that means the temperature to make ice gets lowered. So it's warmer longer because it's got salt in. Does that make sense? How it says salt in. What's my I? If it's sodium chloride? 2. So it's going to lower it kind of twice as much by adding salt, depending on how much salt we add. So this one is a little colder because it's going to get colder faster. Does that make sense? So this one will take a little longer to make ice. It would have to go down to 5 degrees below 0 before it made ice. This one should be turning to ice at 0. Okay? So when you write up, if this is the lab you want to write up, you can just say that the one with salt was warmer. You can say that it's about 5 degrees. The one without salt was already at 0. It should have been making ice soon, but we're going to run out of time. Okay, so write up a lab. You do have a test for me. If you need to know how many things you need left to turn into me, if you're missing labs or tests or whatever, I can tell you if you don't know. If anybody has a question, I can go over a problem. I have 5 minutes. How do you want me to use that 5 minutes? Rachel's already got her stuff put away. So she's done. Anybody have a question? You want me to do another problem? I'm happy to do another problem. No? No one? All right, then just for fun, I'm going to do one more problem. And I'm going to do 11-1 because I have it that I should do 11-1B if I have time, which means there's probably a question on your test that's similar. So let's do, how many liters of a 0.245 molar, a big M, remember, my molar is going to be moles per liter of solution. Okay, so big M is going to be moles per liter. Small m is going to be moles per kilogram. Okay, so how many liters of a 0.245 molar solution of NaCl will be necessary to make 100 grams, oh, I should have the balance equation, 3 NaCl plus AlNO3 turns into AlCl3 plus 3 NaNO3. So they're telling me that I have 0.245 molar solution of this, and they want to know they want to make 100 grams of this. Okay, so they're not asking me about that, I can ignore that. They're not asking me about this, I can ignore that. When I have a balanced equation, I know that for every 3 moles of this, I'm going to get 1 mole of this. That's going to factor in. But when I'm talking about moles to moles, that means I have to convert this first to moles, and I have to have this as moles. So I'm going to start with what I want. So I'm going to start here. So I'm going to do 100.0 grams of AlCl3. I want to convert that to moles, so I want moles on the top and get rid of my grams on the bottom. That's look on the periodic table. 1 aluminum, 3 chlorines. How much does that weigh? 133.5 grams. The grams cancel out. So I'm left with 0.7491 moles of AlCl3. Then I'm going to do that 0.7491 moles of AlCl3. Now I'm going to use the balance equation. For every 1 mole of that, and that goes on the bottom because I want it to cancel out, I'm going to get 3 moles, or need 3 moles of NaCl. 3 moles. So now I've converted from AlCl to moles of NaCl. But I don't want moles of NaCl. I need to know how many moles per liter I have. So that gives me 2.247 moles of NaCl. So now I'm here. I know I'll get 2.247 of them. And so now I have to if this is moles of NaCl over liters of solution, I need to figure out how many liters I have. So this is my moles, so I'm going to start over here. 2.247 moles times, this is, I want my moles to cancel out. So 0.245 moles in 1 liter. I use this number and I just put the moles on the bottom. This goes with the moles and this is over 1 liter. So I put the 2.54 on the bottom so that I'm left with, that cancels out, and I'm left with a liter, liters. So 2.247 divided by 0.245 gets me 9.17 liters of its NaCl. So if I use 9.17 liters, that's a lot, of this and mix it with this, I'm going to get 100 grams of that. Okay, so how I start it where I want to go. I want to go to 100 grams, work backwards. Okay, and just remember that when they give you this mole, big M, it's how many moles per liter. And that's how you get your liters.